One of the most common types of evidence encountered in an arson investigation is fire debris examined for the presence of ignitable liquids. Fire debris testing can determine if an ignitable liquid or its residue is present in the sample, and if it is, testing may be able to further classify the ignitable liquid or residue that is present. This examination is conducted using gas chromatography mass spectrometry. If a comparison sample of similar debris or background information is provided, examination may be able to determine if the compound or compounds detected were naturally occurring in the debris substrate. For example, a questioned sample of burned carpet that may have had an ignitable liquid poured on it can be compared to a sample of the same carpet from another location outside the potential ignitable liquid pour. Examination can then determine if any ignitable liquid compound found in the questioned carpet sample was also in the known comparison sample, thereby ruling out the natural presence of the compound in the carpet itself, rather than from an introduced ignitable liquid. In addition, if a suitable comparison sample is submitted, ignitable liquid compounds present in a questioned sample can be compared to potential sources of the ignitable liquid that were found at the scene. When conducting comparisons between a questioned sample and a known source, the following items are needed for identification to be made. Known sample of a potential source must be a neat liquid, undeteriorated by weathering or exposure to heat. Distribution practices must be known, and studies on the compound must be available. The ASTM standard for fire debris analysis and characterization is E1618 Standard Test Method for Ignitable Liquid Residues in Extracts from Fire Debris Samples by Gas Chromatography Mass Spectrometry. Let's take a look at how GCMS analysis on fire debris is done.
This is our fire debris laboratory. In this laboratory we have various different stations where we analyze or prepare our samples. We have a sample preparation station on the other side. Once our samples are prepared, we then bring them over to our oven where we place it in the oven to heat for a designated period of time. After that heating period, we then need to separate out whatever we're going to extract from that sample using various different techniques, but one method we use is a solvent extraction. That would be performed in our hood. Once the solvent extraction is performed and the compounds are placed into solution, we can then put them onto our gas chromatograph mass spectrometer. What we're primarily looking for in this laboratory are ignitable liquids and their residues. And most of the things that we're looking for are very complex organic mixtures. And this instrument is very powerful at separating out those organic mixtures. Gasoline is a very good example. It's one of the most common ignitable liquid residues that we would detect. Gasoline contains several hundred different compounds. In order to identify gasoline, we need to separate out those compounds and develop a profile. So we would inject the sample into the instrument, separation would take place, and then we would get a readout on the screen. I'll talk about that in a little bit, but first let's talk about sample preparation. Some of the more common issues that we face in the laboratory with fire debris samples for ignitable liquid residue analysis are usually related to packaging. Oftentimes the cans are compromised, the lids aren't on properly. If too much time has passed, the metal cans can rust. And once they rust, they will develop little tiny holes where the vapors are going to escape. The whole purpose of the packaging for ignitable liquid residue analysis is to confine the vapors and hold them into the can. If the integrity of the can is compromised, you're going to lose those over time. And if too much time passes, you're going to lose everything. And some other packaging issues are people not using proper containers. Once in a while, we will get things in paper bags. Paper bags are porous. So the volatile components that we're looking for will evaporate through the bag. It also presents a contamination issue. If different items are packaged in paper bags together, you will get migration of the ignitable liquid vapors from one bag to the other. Certain plastic bags are also unsuitable for packaging purposes, like your typical garbage bag, your typical polyethylene garbage bag. It's not going to seal well, and polyethylene is somewhat porous as well, so vapors will escape. Some other issues, as I mentioned earlier, include overstuffing the can. You don't want to overstuff the can. You want to make sure that you have enough headspace in the can so that we can do our analysis. After we pick up our evidence from the vault, it's brought to this laboratory, to this station, which is our sample preparation station. At this point, we would take a look at the item. If it's in a metal can, we would make sure that the seals are intact, the lid is on properly, and everything is labeled properly as well. Once we're satisfied and everything's documented, we can then take a look inside the can. cut open the seal, open the can. At this stage, I would note the contents of what's in the container because that'll affect how you're going to analyze things later on. You can also, at this point, note whether or not there's any obvious odors. If there's a very strong gasoline odor or if it's a weak gasoline odor, that might affect how you're going to analyze things later. If there's no odor at all, it's also something that we would want to note. We'd then take a carbon strip, put that strip in the can, and seal the can. I'll talk about the significance of that in a moment. I would also pop a hole in the top of the can and then place a piece of metal tape over that hole in order to seal the container. And the reason I'm doing this is for sample preparation purposes. One of the things that we need to do with fire debris analysis is look for ignitable liquid residues. And ignitable liquid residues tend to be volatile organic mixtures. Once this is all sealed up, I would take this can, put it in the oven, heat it up, and then any volatile compounds would go into what's called the headspace above the sample. This is why it's important not to overstuff the cans. If you put too much material in the can, there is no headspace, and you won't be able to get those volatile components into any headspace that would be there, so you wouldn't be able to do your sample analysis. In our laboratory, we do two different types of headspace procedures. One is called just plain heated headspace, which is what we did pop the hole in the top of the can for. During this procedure, we would just take a syringe after heating the can, draw off vapor from the top of the can, and then inject it into our instrument for analysis. We would then seal that up and proceed to our second procedure, which is called passive headspace concentration. That's why we put the carbon strip in the can. Carbon is very good at adsorbing organic compounds. So any volatile compounds that are in the can that go into that headspace will deposit on that carbon strip and concentrate on that strip. So it's inherently more sensitive than the heated headspace technique. Once we're done heating with that carbon strip, we can take the carbon strip out of the can, bring it over to our hood, and elute it with a suitable solvent. Any organic compounds that deposited on that carbon strip would then go into that solvent, which we can then use to introduce into our gas chromatograph mass spectrometer for analysis. So after we've prepared our can, we then take it over to the oven, place it in the oven for a predetermined period of time, depending on what type of analysis we're going to perform and what kind of information we need to get from the sample. If we're doing heated headspace, typically we'd place it in there from anywhere from 15 minutes to about a half hour, depending upon the size of the can and what's in the can. After that period of time, we would then take the can out of the oven while it's still hot, draw off some of that headspace vapor, and inject it into our instrument. Seal the can back up, place it back into the oven to perform a passive headspace procedure using the carbon strip. Once again, we would use another predetermined period of time, usually anywhere from 2 hours to overnight. After that set period of time is up, we would take the can out, let it cool, and then take it over to the hood so that we can remove the carbon strip and elute it with a proper solvent. After we elute our samples, we take the vial that contains the sample and the solvent, place it into our auto sampler on our instrument. At this point, we would set up the instrument to run, get the auto sampler running, and that would take over. The auto sampler would inject the sample into the injection port of the instrument, where the sample would then enter the column, or the analytical column within the instrument. This is a 30-meter column where the separation of all those organic compounds would take place. As the samples go through the column, they're going to interact with the column in different ways. So over time, ideally, you should start separating out individual compounds. Once the compounds separate out, they're passed into the mass selective detector or mass spectrometer. When that occurs, we start to get a readout on the screen on our computer. Ideally, you should get an individual peak for each individual compound. Once we get that readout and everything's complete, we can take a look at the information that's on the screen, go through it, and try to identify what compounds are present. We'll also take a look at the overall pattern. And combining that information, we're going to try to figure out if any ignitable liquid residues are present. If we think that there is something present, we're then going to go into our reference library and then compare the samples to try to identify what type of ignitable liquid might be present. It's important to note that in our environment, there's a lot of things that contain petroleum products just as part of their manufacture. Those things are going to be detected in our samples. They're the same exact things that we would be looking for when we do just our regular analysis. There's also a lot of things that are made from petroleum products, and when they're heated or burned, produce organic compounds that are very similar to many of the things that we're looking at. I think that carpet is a very good example of this. When carpet is burned, the pyrolysis products that come off of that carpet will obscure a lot of the pattern that we're looking at, and it makes it very difficult to figure out if those products are coming from the heating or the burning of the materials, or if they're coming from something that was added to the sample. In some of these situations, it's important to get what's known as a comparison sample. So if you go to an unburned area of the environment that you're in, and using carpet as an example again, pick up a nice clean piece of carpet if that's possible, submit that as a comparison sample, so we can analyze it in conjunction with the samples that were submitted as unknowns. Once our data is obtained and our interpretation is performed, we will then need to report out the results. If we do find an ignitable liquid residue, we will try to classify that ignitable liquid residue according to ASTM guidelines. Typical examples of a positive on a report might include something along the lines that gasoline was detected in item number 1. You might often see things that say something about petroleum distillates or petroleum products in a certain range of class. For example, a medium petroleum product or a medium petroleum distillate. At that point, it's a good idea to provide some sort of an example of what kind of products might be in that range. An example of a medium petroleum distillate would include something like your common paint thinner or a charcoal lighter fluid. There's also various different classes. There's light, there's medium, there's heavy, and there's also a lot of specialty products out there that typically we would put into one of those ranges, and then also provide an example of what that possible ignitable liquid residue is. Sometimes situations arise where we identify components that we think are from an ignitable liquid or a product that's out there, but we do not have it in our database. Unfortunately, when that occurs, we can't report it out as a positive, but this is where the investigator can take over and try to figure out if there is something out there that might have been used. If they have a suspect ignitable liquid, they can then submit it to the laboratory, and we can perform a comparison to see if it is characteristic of what we're finding. Sometimes we have a situation where there is actually an ignitable liquid that's submitted for comparative purposes. If we do analyze it and it is observed to be characteristic or comparable to what we were finding, we would then just place it on the report and mention that it is of the same class and the same type of ignitable liquid residue that was detected in the unknown sample.